Welcome to AI Paper Slop. Learn from your own latents and not from tokens. A Sample Complexity Theory by Daniel J. Korchinski, Alessandro Favero, and Matthew Wire.
Yes, so we are jumping straight into a really dense high-signal analysis today. I mean, to give you the absolute core insight right out of the gate, this paper provides a rigorous mathematical proof for why self-supervised learning models that predict latent representations are, exponentially more data efficient than models predicting raw tokens.
Right, so we're talking about architectures like Data 2vec or the GPay family, as opposed to standard LLMs or diffusion models.
Exactly. And they don't just, observe this as some empirical vibe on a GPU cluster. They actually prove it mathematically using a framework called the random hierarchy model.
Which is huge.
Right. They show that token-level self-supervised learning needs data that scales exponentially with the depth of the data's hierarchical structure. So the sample complexity is basically m to the power of L plus 1.
But if the model predicts its own latents, that requirement just drops.
It drops massively. It becomes a constant size relative to the depth. It just takes m cubed samples.
Wow, m cubed. So going from exponential to polynomial.
Yeah, and they prove this bound through an iterative clustering algorithm, and then they physically implement it in a custom neural network. And finally, they give us the first sample complexity analysis of Data 2vec.
And the implication here is pretty massive for the field, right? Because it suggests that explicitly stacked hierarchical models, which everyone has been racing to build, might actually be, well, completely redundant.
Yeah, totally redundant.
Okay, so let's kind of ground this before we get too deep into the math. Because to really understand why this theoretical breakthrough matters for someone training a frontier model today, we need to look at the massive data gap between biological learners and artificial models.
Oh, yeah. The gap is almost difficult to wrap your head around, honestly.
Right. I mean, I hear the comparison a lot, but mechanically, what is the actual difference there?
Well, look at current state-of-the-art frontier LLMs. They're ingesting anywhere from 10 to the 13th to 10 to the 14th tokens during pre-training.
Which is just a staggering amount of text.
It is. I mean, that volume is more than 5 orders of magnitude beyond what a human child processes before reaching, adult-level linguistic competence.
Right.
So the question keeping researchers up at night isn't just how do we scrape more data from the internet? It's more why are our artificial architectures so incredibly inefficient compared to biological hardware?
And it really fundamentally comes down to the training objective, doesn't it? We force these models to reconstruct the lowest level surface details.
Exactly. Next token prediction for text, or, predicting the noise added to raw pixels for images.
Which is just, it's like trying to understand the plot, the character motivations, and the underlying themes of a complex 2-hour movie by strictly predicting the exact RGB pixel values of the very next frame.
That's a great analogy.
I mean, it would be computationally exhausting, and you'd probably miss the actual story entirely.
You'd completely miss it.
Right.
And that runs counter to what computational neuroscience tells us. Specifically, the theory of predictive coding suggests that the human cortex doesn't bother predicting raw sensory input at that granular level.
It predicts at a higher level.
Right. The cortex seeks to predict its own future abstract activity, so it operates almost entirely in a latent space. Like when you watch a dog run across a park, your brain isn't calculating the precise trajectory of every photon hitting your retina.
No, of course not.
No, it's predicting the abstract concept of the dog's movement.
And to be fair, the machine learning community hasn't been completely blind to this. Over the last 5 years or so, we've seen a growing family of self-supervised methods trying to, instantiate this biological principle in code.
Yeah, definitely.
You have BO, Dino, Data 2vec, and Jan LeCun's GIP architectures. These learn from your own latent models try to lift the prediction target into an increasingly abstract space as training progresses.
And they get fantastic empirical results, right? Especially in vision and audio. But the theoretical understanding of why they work so well and exactly how much they improve data efficiency has been a massive blind spot.
Right. We've had the intuition, but very few rigorous guarantees.
Exactly.
But, biological intuition isn't enough to change how the industry spends billions of dollars on compute clusters.
Yeah.
If we're going to claim that latent prediction is exponentially better, we need intractable mathematical proof.
We need the math.
So how did the authors actually model this to prove it?
Well, to prove a claim about sample complexity, you have to build a theoretical playground where you completely control the exact structure of the data. So the authors use something called the random hierarchy model, or RHM.
CAR-HM.
Think of the RHM as a probabilistic context-free grammar built on a regular fixed tree. It basically generates data from the top down.
Walk me through the mechanics of that tree. Like, what does it actually look like from the root down to the leaves?
Sure, so at the very top, at depth L, you have a root concept. Let's say the underlying meaning of a sentence.
Okay.
This root concept generates a hierarchy of hidden, latent symbols, branching downward layer by layer. It keeps generating these abstract subconcepts until it finally reaches the visible tokens at the bottom.
Which are the leaves.
Right, the leaves of the tree at level 0. These are the actual words or pixels that the model gets to see.
And there are specific parameters governing how this tree branches, right?
Yeah, 2 critical parameters dictate the math here. First is L, which is the total depth of the latent tree, and the second is M, which is the number of production rules per symbol.
Production rules meaning?
You can intuitively think of M as the number of synonyms or variations for any given concept.
Oh, I see.
So if a concept has an M of 5, there are 5 different ways that abstract idea can physically manifest in the layer directly below it.
Okay, I want to pause here and look at the baseline they establish.
Yeah.
Because if I take a standard masked language model, like a typical flat transformer doing token-level masking, and I train it on the visible leaves generated by this RHM tree, the paper says the sample complexity is m to the power of L plus 1.
Yep, m to the power of L plus 1.
Why does it scale exponentially? Like, what is the actual physical mechanism causing the model to need that much data?
It's driven entirely by the dilution of the statistical signal. So in a token-level objective, your observable target is a masked token at level 0, and your context is the surrounding visible tokens, which are also at level 0.
Right.
But to learn the underlying grammar, to actually understand that root concept at depth L, the model has to pick up on the statistical correlations between those surface tokens.
But those surface tokens are only related because they share a hidden ancestor way up in the tree.
Exactly. Which means the statistical correlation has to physically travel all the way up the latent tree from the context tokens to find that shared hidden ancestor, and then travel all the way back down the other side of the tree to the masked target token.
Oh, wow. So every step up or down that tree is a massive loss of signal.
It's actually worse than just a generic loss of signal. Every time the correlation passes through an unresolved production rule, it has to average over those M synonymous choices.
So it gets diluted.
Highly diluted. That attenuates the signal by a factor of M. So in terms of sample complexity, every extra rule you have to resolve costs you a factor of M in data.
Meaning, to learn the highest level rule at depth L, you pay an exponential cost.
You need m to the power of L plus 1 samples just to isolate the signal from the noise.
That paints a really grim picture for current architectures. It basically means token-level prediction is mathematically cursed when it comes to deep hierarchical data.
It is. We are basically brute forcing our way through that exponential decay just by throwing trillions of tokens at the problem.
So how does predicting latents actually shatter this bottleneck? Because it clearly does, according to the paper.
Yeah, so the authors introduce an algorithm to prove the escape route, and they call it Iterative Latent Clustering, or ILC. And unlike the top-down generation of the data, this algorithm works bottom-up.
Bottom-up, okay.
It starts by looking at the visible tokens at level 0. By observing local correlations between nearby tokens, it can identify the level 1 synonym classes. Recovering this first level costs m-cubed samples,
which is a polynomial cost.
Yeah.
And that's pretty standard for learning a single layer of relationships.
Yeah.
But how does it get all the way to the top of the tree without, triggering that exponential tax we just talked about?
Through an incredibly clever mechanism called target lifting.
Target lifting?
Yeah. Once those level 1 latents are recovered, the algorithm stops trying to predict level 0 tokens. It explicitly lifts the prediction target to level 1. So now, both the context it's analyzing and the target it's trying to predict are at the exact same level.
Because they're at the same level, the signal doesn't have to travel all the way back down to the leaves.
Precisely. The statistical strength of the correlation is now identical at every single scale.
Oh, that's elegant.
Right. To learn level 2 from level 1 costs m-cubed samples. To learn level 3 from level 2 costs another m-cubed samples. Every jump up the hierarchy becomes as computationally easy as that very first token level step.
So the result is?
The result is that recovering the entire non-root hierarchy takes on the order of m-cubed samples. The exponential dependence on the tree depth, L, is just completely erased from the equation.
I mean, the magnitude of this claim is just staggering. We aren't talking about a small percentage optimization in training efficiency or like tweaking a learning rate schedule to get a 5% bump.
No, not at all.
This is the difference between polynomial and exponential data scaling. It is the mathematical difference between a problem being completely solvable and practically impossible at scale.
Yeah, and connecting this back to the biological gap we discussed earlier, it provides a mathematical framework for why the human brain is so efficient.
Right.
If biology is utilizing a latent prediction mechanism, it operates on a fundamentally different, exponentially more efficient scaling curve than our current LLMs. We are essentially playing a completely different game.
Okay, but I have to play devil's advocate here for a second, because abstract algorithms on paper are fantastic for theorists. But ML engineers don't run abstract algorithms. They run backpropagation on GPUs.
True.
If this latent lifting is so mathematically superior, why did the entire AI industry standardize on next token prediction in the first place? Like, can we actually build a differentiable neural network that does this without collapsing?
Well, the industry defaulted to token prediction because it's incredibly stable to train.
Stable, yeah.
When you predict a ground truth token, you have a fixed target. But when you predict your own latents, you risk representation collapse.
Where the model just cheats.
Exactly. The model can just decide to map every single input to the exact same continuous vector, achieve a loss of 0, and learn absolutely nothing.
Which is a nightmare to debug.
Oh, a total nightmare. But the authors don't leave us hanging with just a theoretical algorithm. They bridge the gap by introducing the Stacked Latent Clustering Network, or SLC, which proves you can actually do this with gradient descent.
Okay, so how is the SLC structured to mirror the bottom-up approach of the algorithm?
It physically mirrors the ILC algorithm by using a stack of L-1 identical modules, one for each level of the hierarchy.
Okay, so explicitly stacked layers.
Yes. And each of those modules contains two distinct components, a predictor and a clusterer.
Let's break down the mechanics of those two components. What is the predictor actually doing at a given layer?
So the predictor uses a cross-entropy loss to guess cousin tokens. It basically looks at a specific patch of data and tries to predict the representations of neighboring patches.
It's building a statistical map of what tends to co-occur.
Exactly. Then the clusterer takes those prediction vectors and uses a contrastive loss to group them into discrete codes.
So for you listening, the contrastive loss is basically pulling similar contexts into the same cluster while actively pushing dissimilar ones apart. That way, the model doesn't get confused and just lump everything together.
Right. That pulling and pushing is what builds the discrete latents, but, you still have the problem of representation collapse.
How do they fix that?
To prevent the student network from finding that lazy shortcut we talked about, the target it tries to predict comes from a teacher network. And this teacher network uses an exponential moving average, or EMA, of the student's own weights.
Okay, so for those visualizing this, think of the EMA teacher not as a separate, independent entity, but like a mentor who slowly updates their worldview based on a delayed, smoothed-out version of what the student is learning.
I like that analogy.
It prevents the model from changing its mind too frantically, providing a stable, moving target.
Yeah, that's spot on. And when the authors take this explicit stacked architecture and train it end-to-end using standard gradient descent, it perfectly matches the M-cubed theoretical bound.
That's incredible.
The neural network achieves the exact polynomial scaling that the abstract math predicted.
Wait, okay. If I'm tracking this correctly, they physically hard-coded a separate layer module for every level of the hierarchy. Layer 1 hands off to layer 2, layer 2 hands off to layer 3.
Correct.
Doesn't that imply we need to fundamentally redesign our current architectures? Like, does this mean the community needs to abandon standard flat transformers and explicitly stack modules like HDPLA to actually get these gains in practice?
That is the most logical assumption to make, right? And it leads directly to the paper's most surprising finding.
Which is?
The answer is actually no. You might not need explicit stacking at all.
Wait, really?
Yeah, they proved this by running a sample complexity analysis on Data2Vec.
But Data2Vec is a standard flat transformer architecture. It doesn't have hard-coded modules for different hierarchical levels.
It doesn't. Data2Vec is completely standard, not explicitly stacked like the SLC network or the HGPA designs researchers have been exploring. But the authors show that Data2Vec implicitly performs hierarchical latent prediction just by virtue of how its targets are constructed.
I'm trying to wrap my head around that. How can a flat sequence of transformer blocks simulate a stacked layer-by-layer hierarchy? What is the mechanical trick there?
It all comes down to the residual connections and the construction of the prediction targets.
Okay.
In Data 2Vec, the target for the student network isn't just the output of the final layer of the teacher. The target is an average of the top K blocks of the EMA teacher network.
Oh, interesting.
And because transformers use residual connections, that identity path that allows features to skip ahead, a feature decoded in an early block propagates through to all the later blocks.
Right. So that top K average target isn't just a high-level representation. It actually contains a linear component of all the latents the encoder has learned up to that point, from the lowest level all the way to the highest.
Yes, exactly.
Yeah.
Because of that composite target, the training naturally organizes itself into distinct phases.
Phases.
Yeah. At initialization, which we can call phase 0, the model only knows raw tokens. It hasn't learned any abstract concepts yet. So, predicting the teacher's output essentially reduces to basic token-level mask prediction.
It solves that first, then.
Right. It solves this relatively easily and learns the level 1 latents, which costs the expected M-cube samples.
But then the EMA teacher updates based on the student's new weights.
Exactly. The teacher absorbs those newly learned level 1 latents. Suddenly, the composite target the student is trying to predict actually contains structured level 1 latents.
Oh, wow.
The prediction problem has organically lifted itself from the surface leaves to level 1. Phase 1 now begins. The student uses level 1 context to predict level 1 targets, recovering level 2. And this next phase also costs just M-cubed samples.
That is mechanically beautiful. The encoder is basically recursively climbing the hierarchy.
It really is.
It's internally clustering synonyms layer by layer, driven entirely by the delayed reflection of its own EMA teacher. It's almost bootstrapping its way up the tree.
And this isn't just a nice theory either. The authors verified it empirically inside the network.
How did they do that?
They measured the synonym clustering score inside the Data 2Vec encoder during training, and they found that the deeper layers genuinely exhibit stronger clustering of low-level latents. And the transition to learning each new hierarchical level happens almost exactly at that M-cubed sample threshold.
There's a massive structural irony here for the machine learning community then. We've been theorizing about and honestly spending tons of resources trying to build explicitly stacked hierarchical models to force this exact behavior.
Yeah, we thought we had to hand design the abstraction layers.
Exactly. But this paper mathematically suggests that explicit stacking is largely redundant. A single latent prediction module like Data 2Vec naturally climbs the hierarchy phase by phase, just by chasing its own moving average.
It's an incredibly elegant validation of the self-distillation mechanism. It proves that flat architectures are perfectly capable of deep hierarchical learning if the objective function is designed to implicitly lift the targets.
Okay, so if we pull all of these mathematical proofs and architectural mechanics together, what is the core actionable takeaway for the ML engineers and researchers listening today?
The takeaway is that predicting from your own latents amplifies a statistical signal that token-level prediction inherently dilutes.
Right.
For years, we've had the intuition that token-level prediction is wildly suboptimal for data efficiency when dealing with deeply hierarchical data, which, by the way, text, code, and images all are.
Definitely.
This paper proves that intuition quantitatively and definitively. It changes the conversation from latent models seem to learn faster to latent models operate in a fundamentally different mathematical complexity class.
Which brings me to a final, slightly provocative thought for you to mull over as you look at the current trajectory of the field. Right now, the entire AI industry bases its empirical neural scaling laws on the power law decay of token correlations.
Yep. Everything is tokens.
We predict how many billions of dollars we need to spend on our next GPU cluster based entirely on the physics of next token prediction. But if latent supervised generative models are fundamentally operating on an exponentially more efficient scaling curve, this M-cubed trajectory, are we on the verge of a massive paradigm shift?
That's the million-dollar question.
If researchers can figure out how to scale latent prediction seamlessly for generative tasks without representation collapse, are we going to systematically abandon next token prediction entirely? And in doing so, break the very scaling laws that are currently dictating the future of frontier models? I mean, it's a question that could entirely redefine the next generation of architectures.
It fundamentally challenges the prevailing assumption that brute forcing more token data is the only path to smarter models, because the math says there is a smarter way to learn.
A smarter, exponentially more efficient way. Thank you for joining us for this deep dive on AI Paper Swap. We will catch you next time with more signals from the frontier of AI research.